we build everything using gates, right? It's super cool to build stuff using gates. But what about if this circuit is really huge? Huge circuit, right? So in that case, I'm gonna have a huge number of gates are filling everywhere. Then we will have a problem with what? Routing. Do you guys agree? So while you are working for the 2300 lab, right? You bring the ICs, right? And you keep putting what? Wires, connect them from one to the others, and then you connect everything to the VCC. And then you will start looking to the outputs while they are pushing inputs and so on, right? In reality, it's really cool and nice, but what about if the circuit is the processor? Then what I'm gonna do? I'm gonna spend hell of time, and if I missed one wire in the middle of this jungle of wires, I have to go ahead and do what? Pull out all of the wires and actually rewiring. Do you guys agree?
Yeah.
Solving this problem is to add extra abstraction. And these abstractions will help me to decrease number of what? Gates. Make sense? So what does it mean? So, imagine that, we have here something is called transistor level. Transistor level will build us gates. Then we'll start connecting everything together with gates, right? So that's actually what's called gate level. And then, if I would like to combine these gates and building components, then I'm gonna build two things. One is called, two things. That's not the right thing. Two things, which is basically combinational circuit, and this is sequential circuit. What is combinational? What is sequential? So combinational and sequentials are elements in the reality. They are built using gate level, bunch of gates. Combinational is actually straightforward. I give an input. I depend on the response time of the gates to produce an output. Okay? While the sequential circuit, it has the timing as an extra dimension in the circuit. What does it mean? So you will have an input and you will have a source of the time, and then you will get the output based on what? Variation of the time, and they call it clock. So combinational and sequentials, both of them are using what? Gate level implementation, while everything in reality is a transistor level, while transistor actually is silicon. So you are just using semiconductors. So whatever I mentioned now, it makes sense to everybody, or it need more clarification, or what?
Just a little bit more, please.
Again, so
Yes.
we have a piece. We got some sand from the beach, right?
Yes.
And this sand are what? Rich of silicon. Then we took this silicon thing that we went to processing it. We built semiconductors, right? We took the semiconductors and we built what? Transistors. We figure out from the previous presentations and lectures that gates are bunch of what? Transistors, right? So I'm using more what? Gates. So that's called gate level. Now I'm gonna use these gates to build me components. This component is just like relying on the input and response time. That's combinational circuit. If it's actually responding time with the input, that will be sequential circuit. Then use both of sequential and combinational circuit to build a huge circuit like processors, multiprocessors, and so on. Now it makes sense?
Yep, got it. Thank you.
Perfect. Okay, now we're gonna focus on the combinational circuit. Combinational circuit. We mentioned also while we are working with the gate level thing that we have something is called what? Critical path, right? And also we learn everything how you can build it with NAND gate, NOR gate, other gates from the other gate equivalency, and so on. Do you agree? So we need to talk about the first device or element in combinational circuit, and they call it what? Multiplexer. The second element we're gonna learn is called decoder. The third element we're gonna learn is called what? Encoder. And what we're gonna use, whatever we learn from the postulates, K-map, and all of these things to what? Do optimization. So combinationals, we're gonna learn multiplexers, we're gonna learn decoder, we're gonna learn encoders. What does those guys are for and how we're gonna use them? This is basically gonna be the first lecture of the combinational circuit. So the first element we're gonna talk about today is called multiplexer. When I talk about something, we have to discuss what? One, the symbol. Two, truth table. Three, optimization. Four, use case. Okay, so what is multiplexer? Normally, as a circuit designer or the digital logic designer, multiplexer, we use this 3 letters to say MUX. So multiplexer, MUX. If you have one multiplexer, it's a MUX. If you have many of them, MUXes. Okay? Symbol-wise, there is actually multiple version of the multiplexer. But let's look at the simplest one. So the simplest one is the following. Imagine that I have in the DMV, imagine that I have multi roads, and those roads feeding into one road at the end of the day. Like you already have lane here, lane there, lane here, lane there, and all of them going into the same one lane at the end of the day. So that means they're merging, right? We have to follow rules and regulation which one will get into the lane in case all of them arrived at the same time. Do you agree? That's basically what multiplexer actually does. So the multiplexer, the smallest version one, it's called 2x1. What does it mean 2x1? That means I have one input, two inputs. So I have two inputs and I'm producing one what? Output. I0, I1, and O0. So this is the sign for the 2x1 multiplexer. Then we need to decide which one will be taken into the output based on what. So we need a kind of what controller. So here is the part we needed, is called controller. Normally I use select SEL to represent this controller. What is exactly those are for? Those are the resolution of every single input and output in number of bits. So this can be n bit, this can be n bit, this can be n bit, and this can be m bit. So far so good? Hello?
So what is the controller again?
You're gonna see what is a controller. I'm gonna show
Oh,
you.
okay.
Okay, step by step. Okay, now if I assume that n is equal 1, n is equal 1, that means 1 bit, right? So this multiplexer is representing what? Single bit output, single bit input number 1, single bit input number what? 2, and a selector with m bit, and I don't know what is this m and what does select mean. So far so good. This is input 0 and here is 1 and so on. The selector, the size of the selector based on how many inputs I have. Again, so the selector size, how many inputs I have. So from your point of view, how many inputs I have?
2.
2. So then, I will say log 2 of number of inputs is equal m. Okay, here 1, 2. So M is equal to the log 2, 2. So that means it's gonna be 1 bit. So far so good. How are we gonna use it? It's a straightforward. Since this is a single bit, in this case, that means it's 1 bit. Do you guys agree? So if select equals 0, then output is equal I0. So that means this is the official output. If select is equal 1, output is equal I1. So in that case, it's gonna be this way. So who is actually select is the traffic sign, the regulation from DMV. Do you remember when the four-way sign, right? Who is coming from the right? No, the one who comes first, the one who will just go. If all of them came at the same time, then you know the one from the right will start, right? That's basically the DMV regulations. Do you guys remember that? Or you guys forgot how to drive?
Yeah, we forgot how to drive.
Okay. Anyway, so now it makes sense what I am saying. So the selector is telling me what regulation the input will be connected to the output. So imagine that, I have here, oh, sorry. I have here a multiplexer like this, and it has 1, 2, 3, like this, I0 to IN minus 1, right? Inputs, 0, 1, 2, 3, N minus 1. And I have here an output. Let's call the output P. And I need to know the size of what? The select in terms of number of bits. So in this case, M is equal log 2 of what? N. Because 0 to N minus 1 is N, right? That makes sense what I'm saying?
Yes, somewhat, yes.
Sorry, what? 0 to n minus 1 is equal to n?
Yeah, I have a question for you. 0 to 7. How many elements you have?
8.
8, exactly. 0 to N minus 1. How many elements you have?
N.
N.
Exactly. 17 box stacks. Yes. Okay. Sounds good. Now, let's make it 4. So example, we have a multiplexer for X1. So symbol-wise, I0, I1, I2, I3. And this is considered single bit input. So that means, every single wire in front of you is representing 1 bit, okay? The output is P, and this is location 0, 1, 2, 3. So what is the size of the select now? How many bit? It's M bit. And M is equivalent to the log 2. How many inputs I have?
4.
4. So they're going to be 2. So this can actually 2 bit. So if I want to make a table, I can just make a table like this. And I say select when is 1, select when is 0. That means bit 0 and bit 1, right? Because 2 bits, right? If I have like this 2 bit selector, tell me, how many states this table will cover? No.
It will cover 4.
4 states, right? So going to be 1, 2, 3, 4. 0, 1, 0, 1, 0, 0, 1, 1. This is M0. If you remember, this is M1, this is M2, M3. Do you remember the midterms? Now this is the output. So how I'm gonna actually mention it here. When the M0 happens, 0, 0. So pretty much I'm saying that, my output will be I0. Then when M1, my output will be I1. When M2, my output will be I2. When M3, my output will be what? I3. So this is a table describing when the select change, what will be the input connected to be an output. So far, so good?
Yes.
Okay. Then now, we are March 1st, right? Where's March? I cannot see. Here.
Sorry, Professor. I'm trying to just get my head around this, but isn't there four inputs? Oh, sorry, if you just go to the bottom, yeah. So there's 4 inputs, right?
No.
And then you have selector 1, selector 2. That's so the truth table is for the selector.
Yes, because the selector is deciding who's gonna be the output, right? That makes sense?
Okay.
So here is the input.
Mm-hmm. What? So
Those are controlling, right?
So is like another tier from the input?
I'm gonna show you. I understand.
Okay, all right. Okay, got it.
I understand. You are confused because why I didn't put I0, I to the input, right?
Yes. Okay.
I understand, but think about it, right? If I put it, what will happen? We're gonna see, right?
Okay. I'll be waiting. I'll be waiting. Thank you.
At least for now, did you see what's happening?
Yes.
What is this actually multiplexer? It's a controller, connecting between the input and output. I have bunch of inputs and one output. So the selector is doing what? 0.
Choosing.
Oh, it's a turn for I0 to be the output.
Mm-hmm.
1, it's a turn for I1 to be the output. 2, it's a turn for I2 to be the output. 3, it's a turn for I3 to be the output.
Mm-hmm.
That makes sense?
So there's 2 pins going to the selector?
Yes. It's 2 bits. See?
Okay.
M bits. And the M based on what?
The math.
Make sense?
Uh-huh.
Okay. Now, I haven't shown you any gates, right? And we keep saying it's abstraction and bunch of gates and whatever, right? How are we gonna do it? We can start looking into the smallest one. What is the smallest one? 2x1. Do you agree? So here's the 2x1. 0, 1, I0, I1, and here is what? P. And the selector here will be how many bits?
1 bit.
1 bit. And it's called selector, right? So far, so good? So the best way to do it, it's very straightforward, right? We're gonna consider I0 and I1 and P are single bit, right? We're gonna consider all of them single bit. Do you agree? I didn't put here any N or something, right? So one of the way to think about it, if the select is 0, the only one passing is this I0, right? Do you agree?
Yes.
Who is actually allowing me to do this as gate? AND, right? So if I bring an AND gate like this, and I take I0 here, okay? Then I take another AND gate like this, and I take I1 here. If 1 happen here, what will happen? Somebody tell me.
1.
Output will be I0.
Exactly. But if there is 0 happen here, what will happen?
0.
Exactly. So now let's see what exactly I'm doing here, right? So I have a third wire, it's called select. Do you agree? So this is also an input here, select, right? We said when select is equal 0, I0 is P. Do you agree?
Yes.
So I need 1 here. But select here is holding 0. So what should I do?
Oh, a NOT gate.
I have to put here.
Further.
Do you agree?
Hmm?
Make sense?
Yep.
Okay, now I don't want to see I1. I just need to see what? I0, right? So I can just take this here, because in that case that will be 0. So they're going to be 0, and here's I0. Do you agree?
Yes.
Okay, now I just have one output, but this is actually two outputs. So what I can do, OR. So I OR between of them. Why? Look at it, right? I0 ORed with 0. What the output will be?
I0.
Exactly. Now we're gonna change the color and we put here the green. Okay. So select here is instead of 0, it's gonna be what? 1. Okay. When go into the negation, what the output will be?
I1.
0.
Oh, sorry.
And that 1 will go here to make it 1, right? So in this case, I1 will come out, and here it will be what? 0, right? 0 ORed with I1, what the output will be?
I1.
It's gonna be I1. So basically this circuit what realized what? The multiplexer, right? So gate level implementation of the current 2x multiplexer is this circuit, right? Do you agree?
Yeah.
Okay, now let's look to all the critical passes, and then I'll come to show you in the table how can you do it when you put even I and all of these things in the table, and we can make it in a fancy way. Okay, now how many pass I have to the output? I have this pass, right? I have this pass. I have this pass. And I have this pass to the output. Right?
Yep.
Which one is the longest?
The select.
This one.
No.
Because it has not and or. Right? If you know the weight of the time for everyone, you will figure out how much time for this circuit will run. Make sense? If I say that, build the whole entire circuit using NAND gate, you're going to compensate OR with NAND, the NOT gate with NAND, and the AND with NAND, and then you will calculate it as well. Do you agree?
Yep.
Okay. Now, we need to see how can we do it from a traditional way. Somebody's telling me, Professor, select is input, and also I0 and I1 are inputs. Do you agree? Okay. So in this case, I can just make a fancy table, say that, I1 input, I0 input, and select. I'm right? And I have the output P. How many states this table will be covering?
8.
8. Right? So 1, 2, 3, 4, 5, 6, 7, 8. Do you agree? 0, 1, 0, 1, 0, 1, 0, 1. 1, 2, 3, 4. 1, 2, 3, 4. Oh, scheiße, I'm sorry. 1, 2, 3, 4. I made a mistake. 1, 2, 3, 4. Boom. I know what I did. Anyway, 1, 1, 0, 0, 1, 1. Right? This is M0, this is M1, this is M2, this is M3, this is M4, this is M5, this is M6, this is M7. So far, so good?
Can the I0 and the I1 be interchangeable?
Huh? Those are single input, right?
Yes.
Single bit.
So it could the I0 could come in front.
I can make it whatever I want. Which one do you want?
No, that's fine. Yeah.
It's a table, right? I can put everywhere and everywhere, but I have to stick with my rules, right?
Okay.
Anyway, let's try this, okay? Select is equal 0. It mean what? Select is equal 0. It mean I0 will be the output, right? Right? Low.
But I0 is also 0.
Exactly. So this is 0, so he's 0.
Yeah.
Select is equal 1. So the output is what? I1. I1 is 0. Put it 0. Select is equal 0. So that means it's going to be I0. I0 in this case is 1 here. Select is equal 1. It's going to be also what? I1. I1 in this case is 0. I put it 0. Select is equal 0. They're going to be the I0 0. Select is equal 1. So it's going to be I1 1. Select is equal 0. It's going to be I1. Select is equal 1. It's going to be I1. And in this case is equal 1. So we already have a problem, need what? Optimization. So we're going to use what? Our lovely what? K-map.
Okay.
So in this case, here is our lovely K-map. 1, 2, 3. Regulation. What the regulation? Lift up, right? So like this. So going to be here I1, I0, select. Everybody agree with me? Now it's going to be M0, M1, M3, M2, M4, M5, M7, M6, right?
So,
This is the number.
Professor, so the select has to be the least significant bit always.
Huh?
Does the select have to be the least significant bit always?
The select has what?
The least significant bit.
Doesn't matter. I'm gonna make it to you now with a different way, okay?
Okay, sure. Thank you.
Okay. Anyway, so put the select now is equal what? Scheiße. Anyway, so here we're gonna be what? M2. M2 is equal 1, right? M5, 6, and 7 equal 1, right? 5, 6, and 7 equal 1. You guys agree? The rest are what?
Zeros.
Zeros. How many groups I have?
2.
2.
Let's do it. So group 1.
2.
Group 2. So P as a function of select and I1 and I0 is equivalent to group 1 ORed with group 2. Do you agree? So let's do it now. So group 1 is what? It's going to be I0 with select complement. Group 2 is I1. And if you go here, it's going to be select. Which is exactly like what? Right? Make sense? So one of you guys asked about, the order.
Cool.
Right?
That makes sense.
Somebody asking me for the order, right? So let's do the order. I like orders, Here. Scheiße. Anyway, so go here. You want select where?
The most significant bit.
You want it to be in the most significant? Most significant. Select I1, I0, P. 1, 2, 3, 4, 5, 6, 7, 8. 0, 1, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 1, 1, 2, 3, 4, 1, 2, 3, 4, right? M0, M1, M2, M3, M4, M5, M6, M7. You agree? Select equals 0. So no matter what, it's going to be I0, right? So put it. So going to be 0, 1, 0, 1. You agree?
Yeah.
Select is equal 1. It's going to be whatever in 1. It's going to be 0, 0, 1, 1. Super good. Now make the K-map. Here is my K-map. 1, 2, 3. Here we're going to be what? Select I1, I0. 0, 0, 0, 1, 1, 1, 1, 0, 0, 1, 0, 1, 3, 2, 4, 5, 7, 6, right? So M1 is there. M3 there. M6 and 7, right?
Yes.
Give me. What will be?
2 groups.
2 groups, right? So group and group. So, P as a function of select I1, I0 is equivalent to group 1, group 2. Group 1 or with group 2. So group 1 is what? It's going to be select complement ended with I0. And this one is going to be select. And if you go here, we're going to be what?
I1.
I1.
Oh, cool.
What do you think? Is it cool?
That's pretty cool.
Okay. So any question?
Nope.
Anything is confusing? Anything is not confusing? Okay, $15. Okay, anyway. The second topic is, that how many, that you how to build multiplexer as a little one, right? Using, gates. What about if somebody telling you, I have just a bunch of 2x multiplexers and I would like to build an array of 4x multiplexer. So your design need 4x multiplexer, but you just have in your hand 2x multiplexer. What are you gonna do? So basically, required 4x. In my hand available 2x1s. What is my strategy? My strategy is very straightforward, right? 4x, it used to have like this. I0, I1, I2, I3. 0, 1, 2, 3. And here I have selector, and this selector size is what?
2.
2 what? 2 bits.
2 bits.
Be sure that you use this bits because the bit is holding wire. It's a wire. So 2 bits. And I'm going to call it select. And the output is P. Now, whatever I have in my lab, 0, 1, and whatever X, Y, and this is Z, and the selector is going to be what? 1 bit. So my strategy is straightforward. I'm going to use a network of 2x multiplexers. So let's see what is this network 2 multiplexers will be. So imagine the following. I have here, if I use a multiplexer like this, and I put here I0 and I2 here. Okay? Just an example, right? I put I0, I2, right? Then another multiplexer, and they're going to be I1 and I3. 0, 1, 0, 1, and here is the selector. This is 1 bit each, right? Then I will take this and I put it in another multiplexer, and that will be my output, right? If I know this selects is 2 bits, right? So gonna be select bit number 1, select bit number 0. Those are 2 bits, right? Do you agree?
Yep.
So imagine that this one and this one are common. So basically, you're gonna build something called multi-level network, right? So this is a level, so that means they have a common select, and this is a level. It has a different select. Since I have 2 bits, so that means how many levels I have? 2 levels. Make sense?
Yep.
So for instance, if I put here 0, right, what will happen? I'm gonna play it with the trick of this 2 power 0, 2 power 1. Do you see what I'm doing? So 2 power 0 is 1. That's why I make here 1 step distance. 2 power 1 is 2. That's why I put I0, I2 together, because 2 difference between of them. I1 and I3 together, 2 difference between of them. Because 3 minus 1 is 2, 2 minus 0 is 2, right?
Okay.
So in that case, if I put here 0, 0, and I put here 1, what will be, and 0 here, what the output will be? Let's track it, right? So if it's 0, so they're going to be going here up, right? If it's 0, they're going to go in here and up. Do you agree?
Yep.
And if this is 0, so that means this will be selected, so they're going to be I0. Do you guys agree?
Yep.
Then if I put here 1 and here 0, who will be selected this way. So they're going to be
I
right.
You mean
Now
I3?
let's see the 1. So I have here 1. So 1, that means it will be applied in both, right? So 1 here is going to be I2, 1 here is going to be I3. Make sense?
Yep.
So if I put here 0, so I'm talking about this one to going to be I2, and if I put here 1 and 1, so basically this one will be taken, so going to be I3. So pretty much I make it here I0, I1, I2, I3. So pretty much I build using 3x MUX 2x1 to have same effect of the 4x1. Sounds good? So I can come into a very nice regulation rule saying that, if I would like to build nx1 MUX using MUX 2x1, so I need n minus 1 MUX 2x1 to build. With how many levels will be what? Equal m, which is the log 2 of n. Does it make sense?
Kind of.
So it's n plus 1, right? Not n minus 1.
No, it's n minus 1.
0 to n minus 1 is n, right? We mentioned that, right? 0 to 7 is 8, right?
Yeah.
So if I have nx1, that means I have n inputs. I would like to use 2x1 network. So in that case, first of all, I need to define how many levels. How many levels are going to be how many bits of the selector. So it's equivalent to m. And m, it was log 2 of n. Right? While how many x? So basically, if you notice in the 4x1, I need 1, 2, 3. So that's basically what? 4 as an input minus 1, it gives me 3, right? 3 mx21.
Oh, okay.
Any questions?
Sorry, because there's a plus there, so I was confused.
Yeah, I'm fast. Yes. Okay, doke. Any question?
Nope.
Could you move up a little bit, please?
Yeah, sure.
Right
Where?
there. Right
Here?
there. That 3 MUX 2x1. How
Yes.
did you
Huh?
how did you get that again? Could you explain that part?
This one? Here. This is 4x1, right? We know that it's a binary system, right?
Right.
So we have 2 power 0, 2 power 1, 2 power n of the selector, right?
Right.
Do you agree? So 2 power 0, I need 1. 2 power 1, I need 2. 2 power 2, I need 4. Do you agree? So here, I need this level to be 1. 1, I need 2, right? Then, how did I distribute it? 0, so that means, this guys will be distance 1. 2 power 1, that means distance between 2. You see that?
Yeah.
And that's it. I'm going to make 8x1 in front of you now as an extra example.
Oh, okay.
Okay? So now, 8x1. This is what required. Available 2x1. Sounds good? How are we going to do it? Straightforward. Level equivalent to the log 2 of 8. So that means I have what? 3 levels, right? 3 levels, that means what? 3 selectors, right? So it's going to be select 2, select 1, select 0. Do you agree? So here is going to be 2 power 0, 2 power 1, 2 power 2, right? So in the level 2, or right, I'm going to have a 4 multiplex. Let's do it. So going to be here 4. 1, 2, 3, 4. Okay? In a level 1, I need 2. Yes, makes sense too. You know why? Because see, 1, 2. In a level 0, 2 power 0 is 1. Literally, I need 1 here. You agree? Now, each level, it has its own digits. So basically, those guys having the same selector. This guy having the same selector. And this guy has selector. Select 2, select 1, select 0. Right? This is location 0, 1, 0, 1, 1, 0, 1, 0, 1, 0, 1, 0, 1. So far, so good. Now, we need to sort the input, right? That's 8x1. So that means I0 to I7. Do you agree? Hello?
Yes.
Okay, I0 to I7. This is 2 power what? 2, right? So that means distances are 4, right? So going to be I0 to I4, I1 to I5.
Yeah, this man's putting me to
I2
sleep.
to I6, I3 to I7. Huh. So, you know, makes sense what I'm doing? Hello?
Yes.
Yeah.
Okay, now let's see whether that's, you know, whatever is written in front of you makes sense or not, right? So we are gonna, how are we gonna do it? We know that 8x1 is very straightforward, right? Select 2, select 1, select
Can you go up a
0.
little? Okay.
Sorry. What's up?
Okay, I'm good. I just needed to look at it really quick.
Sure. Okay. And
How do you get the order on the eyes on the left? Do you
you see
just
those? 2
They're
power
based
0, 2
correct?
power 1, 2 power 2, right?
uh
So 2 power 2 is what? 4, right? And you know, I have input from I0 to I7. Do you agree?
yes.
So that means every single one will be taken what? For distance. Have you heard about something called distance accelerator? That's a mathematics operation.
No, I don't think I've ever heard about that.
Anyway, you heard about it now. It's a distancing, okay? So what does it mean, distance? Assume the first input I0, right? So what it will be the second I0 plus the weight of this guy, 2 power 2, 4, right? So gonna be I4. So who is the second? I1, right? After I0. Who will be his neighbor? You know, plus 4. So gonna be I5. Then you know, oh, who is the 2? Then you know who's his neighbor? I6. You know, who is after the 2? 3, right? Who's his neighbor? Plus 4, 7. I cover all of them or not? I did.
Yeah, I kind of got the idea now.
Okay.
Okay.
Let's see if it works or not. Maybe it's not working, right? Who knows? So we're gonna have here a thing covering what? 8 states, right? So I0, I1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8. So gonna be here M0, M1, M2, M3, M4, M5, M6, M7. Okay? 0 1 0 1 0 1 0 1 0 0 1 1 0 0 1 1 1 2 3 4 1 2 3 4. You agree? Now I need to see when the select is equal 0. Select 2 is equal 0. Everybody agrees with me? Where is exactly this in this table? This 4 states. Right? Hello?
Yes.
Okay. So select is equal 0. So that means, you know, the output here is going to be I0, I1, I2, I3. Right? Which is correct, kind of, right? Because I need to get them out in the beginning. Because, you know, if I have a multiplexer, 8x1, it will produce me the 4 output to be I0 to I3. Right? Everybody agrees with me?
Sorry, can you repeat that last part again?
Without repeating, if you have a multiplexer like
Sorry.
this,
Yeah.
if you have here I0 to I7, right? And you already have here selector M gonna be log 3, that means 3, right? Log 2 of 8 is 3-bit, right? So you know that, the first iteration 0 to 3 of this will be taken I0, I1, I2, I3, right? Then the second part is gonna be I4, I5, I6, I7. I'm right?
Mm-hmm.
It makes sense to everybody or not? Do you remember when we made the 2x1, I0, and then I1? When we make a 4x1, I0, I1, I2, I3, and so on, right? For 8, it will be what? I0, I1, I2, I3, and 4, and 5, and 6, and 7, right? Anyway, those two guys will be acting as those, right? So if select one is equal 0, so that means I'm covering this too, right? So here it's gonna be what? 0, so they're gonna be I0, and here it's gonna be I2, right? Then you will move forward so you can get the output 0 and 1, so it's gonna be I0 and so on. Does it make any sense?
So the next one will be I2.
Yeah, because that will be flipping it to be I1, right?
Wouldn't the selector be 1, so it would be I2?
Oh, selector is 0. Look, 0. So it's gonna be I0, and here we're gonna be I2. Yes, you're right. So they're gonna be I2.
Okay, cool. Thank you.
Yes. So it should be I2. Yes. And you move forward. Okay. Any question?
So you can also think of selector like a traffic light, correct? Like
Yeah, it's
stop
a
and
traffic
go.
light. It is a
Okay.
traffic light. Yes. Okay, Duke. Any question regarding this subject?
Nope.
So we learned today there is something called combinational circuit. There is something called the sequential circuit. I'm just like summarizing what we learned today. So those guys are extra layer in the top of the gate level for increasing the abstraction, less resources to be used, right? 1 second. Hey, Prof, I will call you in a 5 second. I'm in a lecture. Okay, bye. Okay, Luke. Hello.
Yeah.
Yeah.
So then I made a nice hierarchy. You have a semiconductor. You get the sand, and then you build your semiconductors, and then from silicon, right? And then you start building gates, and then from the gates you start building components. Those components are internally using the response time between the input and output. We call it combinational. If we involve another aspect or dimension, we call it clock, and that will be a timer as the traffic light. For instance, there is a timer inside. Then that we call sequential. And we define the combinational circuit elements as the most famous one as multiplexer, decoder, encoder, and demultiplexers as well. And I need to write it to you here. It's called demultiplexers. Decoders for demultiplexer. Okay, then we start looking into the first element called multiplexers. We looked into the smallest one and we figure out an equation coming out of it for the selectors. We build the multiplexer 2x1 using whatever ways we made, from the logical way to involving the input with the selector as as an input and getting the output. Also, one of you guys requested that we change the position of the inputs in the table to see whether that there is effect or not, and we found out is there is no effect if you just follow the rules while you set up the table for the K-map. Then we start building the multiplexer, bigger size of multiplexers using smaller size of multiplexers with respect of the organizations and the ordering locations. And that's it for today. Is there any questions regarding the lecture. And in the middle also we mentioned something about the critical path for the circuit performing to X1. If you have any questions, I'm more than happy to assist you. If not, we finish the lecture for today.
Oh, quick one. So the multiplexer, the gate logic that you gave us, that's all multiplexer has. All the, like, any multiplexer has the same schematic, I guess.
What do you think? Is there any other multiplexers?
I'm not sure.
There is nothing called multiplexer. It has to be this multiplexer.
Gotcha.
That's a device, right?
Okay, got it. So it's not.
The other way to do enable in the multiplexer, which is something else.
Gotcha. Thank you.
Okay. We can mention
is-
this in the next lecture. Go ahead. Any other questions?
What is the name for the multiplexer? Is it?
What is the need is like routing, right? You want, you have a node, right? And then, you already have two inputs coming into this node, right? How are you going to connect them? In your circuit in ECE2300 level, right? You make a node, right? You bring all of them together and just make a node like this, right? In a computer, we cannot do this because that's actually what violation. If you are moving data from this way and moving data in this way and just put them in a wire, what will happen? This data will do collision, boom, right? So what you need to do, you need to organize the way. You bring them like this, and then the traffic light will say, oh, pass this now or pass this one.
Oh, okay.
Sounds good?
Interesting. Yeah.
So basically, this is, I can tell you literally what multiplexer. For you in the circuit, you did like this, right? This is the multiplexer.
Oh, okay.
Okay?
Mhm.
This is your node in the digital logic. Okay, any other questions? If there is no questions, I would like to thank you for the time and the efforts, with doing the work with 2300. I wish you guys are safe and, sound. And, if you have any questions, I'm more than happy to assist you. Have a wonderful day. Stay safe and God bless you.
Bye, Professor.
Thank you, Professor.
Thank you, guys. Bye-bye.
Hey,
Thank you,
Professor.
Professor.
Yes, thank you.
Your topic about multiplexers today kind of reminded me of there's a gaming console that Nintendo actually released back in the 80s called the
Exactly.
Game & Watch.
Yes.
Yeah. And Game & Watches use a 4x multiplexer to basically handle it based on a crystal clock.
Yes, the crystal come. Yes, exactly.
Yep.
Yes.
I first learned what a multiplexer was based on that, because I was like, oh, well, how does a Game & Watch that is seemingly digital basically handle these kinds of inputs to like
Yes.
a proper distribution?
Yes.
And the same clock that was actually used to handle the alarm that was built on them was also just sped up in order to actually run the game. And I just thought that was super cool, because that was probably like my first introduction, I think, to a multiplexer.
That's pretty cool.
Yeah.
That's pretty cool.
Yeah.
So, hopefully you are enjoying the course,
Yeah, no, totally. I
Thank you, Samuel. I really appreciate it.
Yeah, appreciate it. I'll
Thank
see you
you.
around.
Thank you. Have a good day. God bless. God bless you guys. Thank you.